Let's continue our discussion with the hash function, and in this lecture we will see some practical ways of constructing some hash functions. Let's first of all see how we basically uh, feed the input for the hash function. So the input is divided into n blocks, and each block contains m number of bits. So there are a total of n times m bits, okay, and which are divided into n blocks, each block containing m number of bits. And notation goes like this. So bit number 1 of first block we will call as b11, bit number 2 of first block b21, so on so forth. In general, if you have suppose somewhere here jth block, and inside that we consider ith bit, that will be represented by bij, okay. And one of the simplest way to produce hash of this large data block is like this. We first define a new variable ci, which denotes ith bit of the hash code, where of course I will be equal to 1 to n. And how is it generated? It is generated by simple XOR operation like this. We XOR all the bits, that is the m number of bits in that block. bi1 XOR with bi2 XOR with bi3, so on so forth. And what will we get at the end? We get such c1, c2, cn bits. Now you see the input block has n times m bits, and the hash produced out of this has n bits. As you might already feel this, that it is simply producing actually a parity bit. So it can be used for data integrity, so that we can verify that if data has been changed. But it is not a good hash function. There is not much randomness in it. So in order to introduce more randomness, we need to do some more operations. Such operations may involve like circular shifting operations and some other operations. So let's see one way to do it. So initially set the n bit hash value to 0, then process each successive block of n bits as follows. Then rotate the current hash value to the left by 1 bit, it is a left shift. XOR the block into the hash value. Let's see it with some illustration. Let's take this illustration. Suppose n is equal to 16, that is a data block is broken into 16 parts, and each block, sub block of the data has 8 bits like this. So now what is the first step for this type of hash function? So the first step is to initialize all of them to 0. Okay, so there are 16 such bits, we initialize to 0. And what is the next step? Rotate the current hash value to the left by 1 bit. So when we will do that operation with all zeros, nothing will change. So you shift 0 and to the left. So this one you will need to do the cyclic shift here. So nothing is changed. After that, XOR the block into hash value. That is, take one block at a time. Suppose take the first block, this one. Fine. So we'll do XOR. So basically it will have some bits, 8 bits. So b11 XOR with b12 XOR with b18. Okay, XOR them. Whatever you get, put that in this. So you get here c1. Okay. Now after doing this, you have to repeat this step. Rotate the current hash value to the left again. So now this c1 will be shifted here. So in the next iteration you will get something like this. So this c1 will be here, all others will be 0. Now take second block, XOR all the bits in this block, you will get c2, and put c2 in the second position here. So you get c2, and after that perform the next step, that shift this c2 to the left. So C2 will be shifted here, 0 to here, this 0 will be shifted here, C1 will be shifted here. What you will get? You will get like this. So C2 will come here, fine, and this 0 will come here, C1 will come here, all others are 0, fine. Now we'll take third block, XOR all the bits of third block. Whatever you get, name that C3, and C3 will be put in the third position, so C3 will be here. And after that, give a cyclic shift, one to the left. Okay, so shift everything here, and this C2 will be shifted now here. So what will we get? So we will get 0 here, and then C3 here, then again 0, 0, 0, and here we will get C2, we will get 0, we will get C1, and again 0 here, fine. Then take the next block, suppose C4, XOR all the bits, whatever you get, store it the fourth position. So C1, C2, C3, at least C4 should be here. Then again do the side, this left shift. Okay, shift the one bit by left, and when you do that, 0 will be back here. So what will happen? C3 will come here, and 0 here, then C4, then all zeros, and here you will get 0 here, C2 here, then 0, then C1, then all zeros again. Then you take the fifth block, you will get C5 here, and then you have to do again one bit left shift, and C3 will be here. So what will you get? So you will get 0 here, C4, C5, 0 till this point, then 0, C1, 0, C2, 0, and this C3 back here. Then so 1, 2, 3, 4, 5, and 6, then you have to put C6 here, and like that you continue. What will be the end result even if you see at this iteration? So initially, if you go back to this basic hash, you get a straightforward block of bits like this: C1, C2, C3, and C16. Suppose if n is equal to 16. So there is not much randomization here. Whereas when you will do this operation, see at this step, you actually should have C1 here, but you are getting 0, here C4, C5, then C6, C1, C2, C3. When you will repeat it, you will see that there is a sufficient randomization which has taken place. Okay, so this makes hash function a little bit more robust for data integrity. Now this type of hash is still not suitable for security purposes. So what you can do is, suppose you have this M is the message which contains n times m bits. So let's suppose the original message, this one, let's say this is your M. Okay, and what you will get at the end will be h of m. Okay, so if you take this simple hash example, okay, so this XOR of all the bits of each block is C1, similarly C2. This whole block is now you see a hash, and as has been told, see, the input block can have any size. So this m number of bits, you can vary. Okay, so this n you have to fix, n is fixed, but m is something arbitrary. Okay, so suppose in this example you took n is equal to 16, m is equal to 8. You can also take m is equal to some 32. Nothing wrong in that. Okay, so it's up to you, but n should be fixed because you have to produce hash of fixed length for every data input, that is h of m. And then you can encrypt this hash using some secret key. And then what you have seen in the previous videos regarding message authentication or even digital signature, so this hashing procedure can be used for that. Although It is a very simple hashing technique, very simple, and cryptographically it is not so robust. There are more techniques. We'll see. We'll do at least one of them. So that way we can produce more robust hashing of the message, but this is also sufficient for providing basic message authentication, or suppose how to get digital signature out of it. So you can use private key of some user A, and you can use public key of user A, and you can encrypt this hash using private key, and then you can concatenate this with the message and transmit. And what receiver can do, receiver knows that this has been encrypted using private key, so receiver will try to decrypt this whole thing using public key. Okay, and then verify that after decryption you will get basically H of M. That is what public key cryptography is all about. And receiver knows that message is embedded with it, so it will also compute H of M and check that if they are same. If they are same, it means that we have verified that this data has been received from user A, which is a digital signature. Or if you use just public key cryptography, symmetric cryptography, that is you use some DES or AES algorithm, then you can do data integration or message authentication using this. Now fine, so we have seen several ways of producing the hash, and there are many more ways, but there are some general requirements, especially for hash functions, which can be used for cryptographic purposes. So here is what we summarize it here. First of all, mathematical notation. So the block of data which you provide as input will be represented by X, the block of data for which you have to find hash. And hash is defined like a function h of x. Okay, so practically it computes some operations like we have seen the XOR and cyclic shifts. So mathematically this is the way to define it. Now what are the conditions for cryptographically strong hash function? First is variable input size. As I have told, I will again repeat. If you go back here, so suppose you can take sometimes m is equal to 8, you can take sometimes m is equal to 32, m is equal to any other value, but n should be fixed. So that way you have variable input size. Okay, let's say you are taking n is equal to 16, m is equal to 8. You can take next slot n is equal to 16, m is equal to 4, because what you have to finally do. So it means in the first case you have 16 blocks, each block contains 8 bits, right? And to produce a simple hash you have to XOR all these 8. In second case you have 16 blocks but each containing just 4 bits, and you have to XOR these 4 bits. What will happen? This will also produce 16-bit hash, right? See, when you XOR all 8 bits you get 1 bit. There are 16 such blocks, you get 16 bits. When you have these 4 bits, you XOR them, you get again 1 bit. There are 16 such blocks, you get 16 bits. In both the cases the hash size remains the same. So it is preferred to have variable input size and fixed output size. So this is written here. Now efficiency. The hash should be relatively easy to compute for any given x, making both hardware and software implementations practical. If you can see, XOR is not a big deal, and one left cyclic shift is also not a big deal, very easy to implement. Then there is one important property which we call pre-image resistant one-way property. What does it mean? For any given hash value h, it is computationally infeasible to find y such that h of y is equal to h. Let me write here mathematically. Suppose you have h of x, fine, as a function. So if you see its inverse, it is actually written as this h inverse. So if h of this is equal to y, fine, so h inverse of y will be equal to x, right? So this operation should be computationally infeasible. And if you have done the basic set theory and function, we say that this is x, suppose this is h of x. Given h of x, this x is called a pre-image in mathematics, okay, in basic calculus. So that is the property name, pre-image resistant, one-way property. One-way property means given x, it should be very easy to compute h of x, but given h of x, it should be very difficult to tell what is the x. You can see here, even with a very simple XOR example. Suppose I tell you C1 is some 1 or 0. From this information, even I tell you C2 is some 0, C3 is 1. It is very hard to get what was individual value of each bit B1, BI1, BI2, BI3. Very hard, right? So this property is satisfied by even this simple hash function. This another property is second pre-image resistant, also called weak collision resistant. What does it mean? Suppose you have a block X. It should be computationally infeasible to find Y which is not equal to X with h of Y is equal to h of X. Let's see from the set viewpoint. Suppose you have X and you have Y. Fine. So it means that it should be computationally very difficult to find X and Y such that both produce the same value H. Okay. In other words, you have X not equal to Y, but h of X equal to h of Y. Finding such Y, given one X, finding such Y should be computationally very hard, very difficult. If you are able to do this with any of the hash type of function, it means your hash function is second pre-image resistant, also called weak collision resistant. Okay. Collision here means that the value of h and y, h of X is colliding with each other. Now another property which looks like very similar to this is collision resistant or strong collision resistant. See here, X is given in previous property, X for any given block X. It is computationally infeasible, that is very difficult to find Y such that this. Now it is computationally infeasible to find any pair XY with X not equal to Y such that h of X. See, what does it mean? What is difference? Second pre-image resistant means, suppose some X is given to you. Let's say X is this 1 0 1 1 1 0. Now this X is given to you, it's fixed X. Now it should be very difficult to find some Y, okay, some any sequence of binary such that h of X and also Y should not be equal to X, h of X equal to h of Y. Finding such Y should be computationally difficult. This is this property, second pre-image resistant or weak collision. What is strong collision? That it is not fixed, any X, no, nothing is fixed. So you should not be able to find X and Y. The only thing will be given to you is the length of X and Y. So it should be true for any pair of X and Y such that as long as X not equal to Y, you should not be able to find any such pair such that h of X is equal to Y. Of course, this strong collision resistant is a general property than this, is more stronger. If this is satisfied, the weak collision resistant property is automatically satisfied. And the last property is pseudo randomness, that is output of H meets standard tests for pseudo randomnesses. We have discussed it in the class, lot of tests of pseudo randomness. So this video lecture gives you not a complete view, but at least a basic insight of how hash is produced. I will repeat. One of the simplest ways of generating hash of a data block is, the first step is break the data block into n number of blocks. Okay, n, and this n should be now kept fixed because this will be number of bits in hash, and we want hash to be fixed like. In each block there will be m number of bits. This you can vary. Okay, suppose you have a long stream of binary data coming in, you can choose sometimes m4, m8, m32, you can vary it, but number of blocks should be kept fixed. Then there are various ways. One of the ways is simply XOR bits with each other in each block, and if there are n blocks, you will get n number of bits. This n number of bits will be the hash value of data. Or you can add a little bit complexity. Initialize all the hash bits to 0. Then compute hash of block 1, save it in position 1. Then do a left cyclic shift. Then compute hash of block 2. Then put it in this position 2. Then do a cyclic shift, and so on and so forth. Do this till all the blocks are being computed. you will get a little bit randomization with this. Okay, and then you can also encrypt this hash. If you encrypt this hash with symmetric cryptographic algorithms like DSES, you can use it for message authentication. If you encrypt this hash with private key, you can use this for digital signature purposes. And finally, we did some properties of hash function. One is input should be variable size, not necessary, but it is preferable. And output should be fixed size. That is very important. It is necessary property. The hash output should always be of same size. Efficiency means that it should be very easy to compute hash. XOR operations, cyclic shifts. Pre-image resistant. That is, if you are given the hash value, you should not be able to tell what was the data block easily. It should be computationally infeasible. Second, pre-image resistant or weak collision resistant means if you are given some input block fixed is given to you. Now you should not be able to find, or it should be very difficult to find some other y not equal to x such that hash of both h of y and h of x is same. Then strong collision resistant or collision resistant is that you should not be able to find any pair. It's not like x is given to you. No. The only thing will be that you will be knowing the block size is suppose 16-bit or 32-bit. That is it. Then you have to ensure all the possible 32 such bits. All such 32 bits you can find. No two unequal data blocks should have same hash. It is strong property. And the hash should satisfy some pseudo-randomness properties, some tests which we have briefly done in our random number generation. Thank you.